Okay, so far we talked about the cylinder design, we talked about the piston design, we also talked about the components of internal combustion engine. Now we are going to talk about the connecting rod design. And in connecting rod design, we had to decide what is the size, length, shape, and so on. So design of connecting rod. So this is the piston. Piston is a hollow cylinder, and there is this piston pin, and here this is where the connecting rod is. So connecting rod, if you look at the side view of the connecting rod, this is how the connecting rod looks like. So when we design the connecting rod, first we decide cross section of the connecting rod. Crank pin, and piston pin dimensions, bolt size, and cap thickness. So this is cap. The bolt. This is the cross section. This is the piston pin. This is the crank pin. So how do we design? The design is based on the strength, buckling, and the loads that come on the connecting rod. Now, as you know, the piston is reciprocating at very high velocity. So the inertia loads are quite high. Inertia loads are quite high. Then the cross section is typically of H or I type section, and the reason for this H and I type section is clearly this section is quite strong, especially to bending, because if you look at, so I, which is moment of inertia, and W, which is weight. So I by W ratio is high for I section and typically T section. So you would notice the connecting rods are usually designed using this particular type of section. Now let's look at step 1. It's determination of cross section. So most of the times connecting rod has this I cross section, and this I cross section is also particular proportions. So these proportions are quite common. This thickness is T, this thickness is 3T, then this is 4T, this is x-axis and this is y-axis. This is y, x. And if you look at this particular cross section, looking at the proportions, value of Ixx is equal to 4 times value of Iyy. And here an important aspect is the buckling, because if you look at the connecting rod, continuously on the connecting rod you are going to have compressive loads, but these are not steady compressive loads. They are like impinging or attacking or sort of fatiguing compressive loads. So what we want to make sure is this connecting rod does not buckle or bend in plane under the action of this loading. So for that, what we do is we find out something called as the buckling load, WB. WB is compressive stress multiplied by area divided by 1 plus A length divided by Kxx square, where Kxx is the radius of gyration. So Kxx is the radius of gyration. And the second one is sigma c times a L kyy square. This is about xx. Please notice that's why we have kxx. About yy. That's why we have yy. And a is a material constant. So for an example, a is equal to 1 divided by 7500 for mild steel. A 1 divided by 1600 for cast iron, and A 1 divided by 9000 for wrought iron. And you will notice that WXX, so WB, and I'm going to call this WBXX, and I'm going to call this WBYY. WBXX is less than WBYY. Now,
What is A again?
A is the material parameter. Material.
What's its units?
Let me quickly tell you what the unit is. Its unit is going to be, it would be dimensionless, because L is the length of the connecting rod. Length of connecting rod. Radius of gyration kxx is radius. So which means length of the connecting rod will be in, say, meters. Radius of gyration would be in meters. So what we have is, we have this L by K ratio that is going to be dimensionless. And at the end of the day, what I want you to think about is this equation is nothing but stress multiplied by area is equal to load. Now stress multiplied by area, sigma c times A, is stress multiplied by area, and you are dividing that by this factor which deals with the material resistance to buckling. It again, how long the or tall the structure is, because please try to understand, longer the structure, its buckling strength reduces because it will buckle under much less load. If you have a compact structure, a short structure, then it has higher buckling resistance. So the taller the structure is, so in other words, if the length of the connecting rod is quite high, then it will have less buckling strength. Now, what we do here is we find out WB maximum, which is maximum gas load. So this is maximum gas load. Multiplied by a factor of safety. Now, why is this factor of safety considered? Many a times we do not know exactly what would be the maximum gas load. So to compensate for sort of assumptions, to compensate for material properties, material impurities, and just to take into account the inertia effects, you have this factor of safety, And please understand this factor of safety is quite large, 5 to 6. So what it means is we find the total gas load, multiply that by a 6, we make it 6 times, and then we treat that as the maximum buckling load. So Fg max is equal to P max multiplied by pi by 4 d square. And now we will equate left hand side is equal to right hand side. So Wb max is equal to sigma C times A divided by 1 plus A L divided by Kxx square. Now, since this cross section is a standard cross section, we can find out this entire area in terms of T, because think about it that there are 3 areas. So we have this area on top, we have this area on bottom, and we have this area. So T times T plus 2 times 4T times T. And sigma C for that particular material will be known. You know what type of connecting rod you are going to use. So for small engines, you use cast iron. For sort of larger engines, you use alloy, a special purpose alloy, where that makes that cast iron lighter, easier to flow, easier to cast, and stronger. And sigma C is known. A is known. And from here, we can find value of T. So this is a standard procedure, but many a times what happens is the connecting rod design properties are given in the design data book. So what we do is we look at the load ratings, find out the appropriate connecting rod section, and then actually check if that connecting rod is safe or not. So that is a standard way of doing it.
Refer to the design data book and or the tables and stuff is to do the calculation.
Yes, usually that is, I tell you the reason for that, because unless you are designing the engine or a mechanical component from ground up, it's very expensive to build the components as per your specs. So what we do is once we have some rough idea of what the cross sections are going to look like, what the material is going to look like, we are going to look at the design data book, or we are going to look at the MacMaster, or we are going to look at the Vishay, or we are going to look at Granger and see what components are available. And then we try to use those that will reduce the cost significantly. And believe it or not, this is very important, because if you look at these tons and tons of American and Chinese and Japanese car, they use the same type of parts. So even some parts could be slightly different, there will be some modification, but most of the times the parts are mass manufactured in companies like China, Taiwan, or Mexico. However, there are some specialty parts that are not mass manufactured that you have to get from the dealer, and you will realize those dealer parts are very, very expensive compared to this off-the-shelf off-market parts. So as far as the engineers are concerned, once we understand this is how our design is going to look like, this is the material that we want, these are the dimensions that we want, then we go and get the catalog items. Many a times those catalog items will be slightly off dimensions, then we have two choices. Either we modify the design so that that catalog item can fit, it would be a drop-in replacement, or we will actually try for some minimal machining on that off-the-shelf part that would reduce the cost of the overall product. So remember this, when you go to design, very rarely you will design or you will actually do something from scratch. You will design, you will have rough dimensions, and then you will go and try to get a catalog item. If you don't find the catalog item, you'll find a catalog item that is close or that can be modified and then actually use that. So that's why a design data book is always used in design. 10-15 years ago, when I was actually doing design, we used to have these thick design data books. Nowadays, there are just softwares. So there are special design softwares, these are design databases, there are material databases. So what you do is, once you start designing, you basically put in some preliminary dimensions and software will automatically give you the options that are available, cost, then typical reliability, the grade, and so on. Because that is also very important. We didn't talk about this, but think about why these automotive engines can go for 200,000 miles. Because when they design, what they do is they actually find out the reliability of each component. What that means is, if you go and select a catalog item, connecting rod, that connecting rod will be tested by the manufacturer. Many a times that connecting rod would be tested by some lab, like underwriting lab, or maybe equivalent lab, or maybe a mill standard. And that will tell you that this part has 10,000 hours of life. So this will not break under the regular operating conditions for 10,000 hours. So that actually tells you what is the cycle that it can sustain. And then what you do is, you based on, it's for entire engine or entire component, what you do is you trace the reliability. So you take the reliability of connecting rod, reliability of bearing, reliability of all other components, and at the end, you have sort of a mathematical equation that tells you that how long this engine would perform without any failure. For automotive engines, it may not be a big issue, but for aircraft engines, that's why every 8 years, they have to strip the whole thing down and actually retrofit it or repurpose it or test it. So every single component, every single turbine blade that goes onto the aircraft is tested. It goes through some goes through destructive testing, and all of them, they go through non-destructive testing and X-ray, just to make sure that component can perform. That's why the aircraft components are super duper expensive. That reminds me, if some of you are looking for jobs in mechanical industry, Able Engineering, which is right here next to the airport, is hiring engineers. So they actually are into refurbishing and designing components for aircrafts and rotary wing planes. I mean, rotary wing helicopters and planes. So the next part is design of a big end. So gas load, pi by 4 d square times p, which is p is the p max gas pressure. Then d is the piston dia. dc is the dia of crank pin. And LC is the length of the crank pin. PBC, bearing pressure, LC by DC is 1.25. PBC is equal to FL DC LC. F1 is MR So the maximum value of cosine theta is 1. So if you substitute cosine theta is equal to 1 and cosine 2 theta is equal to 1, this is the maximum wearing load. Force on the bolt. F1 divided by number of bolts. Typically, for connecting rod, they use 2 number of bolts. So typically, N is equal to 2. So you would have pi by 4 dB square sigma t times 2. The next thing is thickness of big end. For that, moment is equal to force times the distance x, sigma b is equal to mc so if you look at the big end, so this is the big end. This dimension is b. And this dimension is t. Okay, so with this, we can solve one problem. Design a connecting rod. .15 mass of the piston 2.25 L LS compression ratio factor of safety so for these parameters we have to find out the cross section. So if you have the standard dimensions, area is 11t square, Ixx is 419, and this comes from the data book. Iyy 131 and ratio of Ixx Iyy 3.2. Next step, gas load. Factor of safety. So WB and then what we do is we use this relation where A is the area, Kxx is the radius of gyration, Ixx is the moment of inertia. So we get a relationship for Kxx in terms of T. And next, the crank radius is equal to 190 divided by 2, that is given 95 millimeter. As the stroke length, (190 millimeter). Length of the connecting rod, then what we do is we use this equation WB sigma C times A 1 plus A L divided by KXX square. Width at big end Now next part is big end bearing. So F 24.7 10 to the power 3 is equal to DC times sigma B. And I'm going to assume LC by DC is equal to 1.3, which is length to dia ratio. So this will become 2 times dp square by 15. Diameter of the pin is 29 millimeter. We use the bearing stress sigma B as 15 Newton per millimeter assume. Then we have to find out the bolt sizes. Are two bolts. So thickness of the big end cap. So this is 44. Sigma. So the moment is 13260. So thickness is 12 millimeter. So that is how you would design a connecting rod. I will quickly go through the design steps. So connecting rod is an important part that takes the reciprocating motion of the piston and converts into rotary motion of the crank. And connecting rod has small end and it also has a big end. So small end fits inside the piston and the big end fits onto the crank pin. So when we design the connecting rod, we have to decide all the dimensions. Also at the same time, we have to decide the bolt sizes, cap thickness, and so on. So design is always based on strength, buckling, and load consideration. And there are typically standard dimensions for the connecting rod. And with those standard dimensions, pretty much the properties of the section are already known. The only thing that we don't know is the length of the connecting rod, which is L, A, which is the material number, and sigma C. So once we decide what is the material of the connecting rod, what is the length of the connecting rod, pretty much we know the buckling strength of the connecting rod. Then basically we want to make sure that the connecting rod is able to sustain the maximum gas load multiplied by a factor of safety, which is about 5 to 6. And then once you equate, everything is known in terms of T, and you can find out the value of T. So for design of big end, we look at the gas load, and then we look at, we assume the ratio between the length and the diameter of the pin. And then we find out for certain bearing pressure, what would be the diameter and the length. We have to find out the maximum bearing load, because as the connecting rod is reciprocating, it has a small mass in the top end. So we need to make sure that the bearing load is able to sustain, the connecting rod is able to sustain the bearing load. If you open the textbook, this is how the connecting rod would look like. Page 1182 gives you a nice picture of the connecting rod, 2 bolts and piston. So for the forces on the bolt, we actually find out, typically there are 2 bolts, and then to find out the design of the cap or the big end, what we do is we find out the maximum bending moment. In this example, we are designing a connecting rod, And this connecting rod has the standard dimensions. All the major properties and proportions are given to us. Length of the connecting rod is given to us. The stroke length LS is given to us. Compression ratio is given to us. Step 1, we find the maximum gas load. We find out the moment of inertia. We find out the radius of gyration. Plug in those numbers in here and then get the value of the thickness. Then in the second step, we consider 2 bolts. We find out the varying load and then we equate that to the load that is sustained by the bolts, because bolts would keep the connecting rod and the big end in place. So bolts are designed based on the tensile criteria. So here we get the 10 millimeter bolt. To find out the thickness of the big end cap, we look at the bending moment on the connecting rod big end, and the maximum bending moment is equated to the section modulus. So once we equate that, we are going to get the thickness. And this is pretty much design of the connecting rod. Now what I want to do is, if you have the textbook, I just want to go through the connecting, the crankshaft design. And crankshaft design is exactly same as the shaft design. Only thing is, the difference is depending upon the configuration of the connecting rod, depending upon the configuration of the engine, the crank could be both sides supported, simply supported, or it could be cantilevered. So crankshaft design, it's a shaft, by the way. Shaft design is similar to shaft design. So you have to find out the forces. You have to find out the bending moment maximum. You have to find out the torque. You have to find out the torque equivalent. And then finally, tau. And then you get the diameter of the shaft. So if you look at page 1161, you will see 2 configurations of the crankshaft. One is the side crankshaft, which is very common in small engines like Weed-Wacker engine, and you have the center crankshaft, which is typically for high power engines. So this is the side crankshaft. This is the center crankshaft. And then if you look at the design process, what you will do is, again, it totally depends upon whether you have a side crankshaft or a center crankshaft, but the process is the same. It's exactly like shaft design. You would find out the maximum load, you'll find out the reactions, then you'll find out the maximum bending moment, and then what you will do is you'll find out the T equivalent and then find out the diameter of the crankshaft. And again, if you have the textbook, I would like to quickly go through page 1161. There are different materials for the crankshaft. Those are listed on page 1161. Bearing pressure is an important criteria to design the crank pin dimension. And in section 32.19, design process for the crankshaft is given. So it will first magnitude, supports, and then the web thickness, they are empirical dimensions, distances, bending shear stresses. So that is the same process. And depending upon whether it's a center crankshaft or a side crankshaft, the procedure gets slightly different, but I would encourage you to review this material, and you'll realize that the process is exactly same as the crank design. The only thing is you will have to find out the loads separately. So section 32.20 talks about the design of center crankshaft. 32.21 talks about the design of overhung crankshaft. And again, then there are a couple of examples that actually talk about the design. The last part, which I want to quickly talk about, is please look at section 32.22. Section 32.22. That talks about design of valve gear. Now, believe it or not, we have done this, because if you look at on the one side, you have design of springs that we have covered. Then lever. So we have designed springs for the valve mechanism. We have designed the lever for the valve mechanism. The only thing is, if you look at, there are different types of valves. There is a poppet valve, page 1192. Then there is mushroom valve, and depending upon the mean gas velocity, you have different designs. So please take a look at it. The next thing is the rocker arm. Rocker arm is just a very simple lever. So it's like a offset lever, and that is designed based on the bending criteria. And then you will see in next few sections, they have actually worked out the design, wherein they have designed the lever, they have designed the spring, and they have designed the pins. So that is the only thing which I want to talk about is I want you to look at page 1210. You will see the lift profile for cam. And then you will see figure 32.33. This is how you design the cam. Now, the easiest way to design something like this is by means of the software. Remember the Lotus engine simulation, it has a cam design module. So basically what you do is you substitute what is the valve opening, what is the valve closing, what type of profile that displacement should be, like it should be a simple harmonic, it should be linear, or it could be constant acceleration, whatever. And then you can actually decide the base circle, the primary dimension of the circle on which that cam is constructed, and it will actually generate the cam for you. So again, in this textbook, explicit process for cam design is not given, but if you were to look at the Lotus engine simulation software, it's a fantastic option for cam design, and you should be able to design the cams. Now, we have finished about 70% of this textbook, and I promise you that if you read through the other topics, you will realize the fundamental principles that are used in designs are exactly the same. This is a very important textbook if you try to go into the design, or if you interview for a product design, if you interview for a robotic system designer, where you design the mechanical components of robots. The information that you studied in this course is going to be extremely useful. So please keep these notes, and please keep this textbook and go back and refer to it as and when needed if you want to prep for some quizzes or exams. Once again, once you go to industry, you will realize we design using computer. Very rarely we actually go and do pen and paper design. But that is where everything is started. Once you have preliminary dimensions, you finalize those, create the CAD drawings, analyze those using finite element analysis. So with that, I'm going to stop here, and I would be happy to answer